All right, howdy everybody. Sorry for the audible here and switching the class around. Completely forgot about the conference. But yeah, we'll start up again next week. This lecture, I just want to review the exam one questions, and then we'll also go over a little bit on the project for this semester too, that you'll see more information at the end of this. Okay, so let me move some stuff around here because okay. Anyways, so yeah, we switched the schedule around just a bit. We are here today, October 19th. So yeah, the exam review is going to be today. Fall break we stuck with here. So on the 24th, we'll begin talking about shallow foundations, and we'll just have to shift everything over. You'll see there's some project work days and a few float days here towards the end of the semester. So we'll probably just might have to take up one of those. But yeah, we should be okay still, even with the shift. I'm still grading the exams, so yeah, I'll try to have those as done as shortly and soon as possible. I did want to share on October 26th, the 31st, and the 2nd, we will not be having in-person lectures. These are going to be recorded. I'll try to do live recordings. But yeah, I need to travel during that time. So yeah, we won't have in-person lectures during those days. So all recorded similar to this one. And I'll try to do the live ones and send the links so you can log in and ask questions still. Okay, let me see. Can I actually move this? All right, good, good, good. Let me move all these things. I don't know why my mouse isn't working. Anyways, all right, so this first problem for your exam, there's three-parter. Where you're asked to find the overconsolidation ratio of the clay, the primary consolidation settlement under the footing load, and then the elastic settlement of the sand layer. So this is only the sand layer here under the center of the footing. So I gave you the consolidation test data. The first thing what we need to do to find the overconsolidation ratio is to find the current effective stress as well as the pre-consolidation pressure, or sigma C. So to do that, we need to plot our void ratio versus our stress, and this was all given to you. And obviously, it's going to be dependent on how you did this procedure here, but the goal is to find the overconsolidation, or sorry, the pre-consolidation pressure. So if you remember how that goes using the Casagrande method is you first look for that point of maximum curvature, so the point at which the curve curves the most, where the trend line changes. Then you go through that whole fun process of intersecting, drawing the straight lines, and then the bisecting angles, and you can find your sigma C, which is your pre-consolidation pressure. So based off of this, we're going to assume the pre-consolidation pressure is somewhere between 310 kPa. Remember, this is in log scale, so this is 200 right here, and that's 300. You have to follow the tracks accordingly, or the tick marks accordingly. So our overconsolidation ratio, this is just the ratio or the pre-consolidation pressure divided by the current effective stress. So our current effective stress here, I'll follow through all of these. We are given the dry conditions at the top. But we're also given a moisture content. So we need to find the moisture unit weight, or the moist unit weight in this first layer. So if we need to find this at where the soil sample was collected, which is down here at an elevation of 8, we know this is 2 meters for this first layer. This second one, elevation of 18 and 10, so this is 8 meters. This is 8 meters right here. And then under that, we have 2 meters since it's only halfway, and the unit weight is 21. We need to find the effective stress, so we have to subtract out the pore water pressure. So this is 10 meters since we have 18 to 8 here, where our groundwater table is. So what we get from this is our in situ effective stress is 145 0.5 kilonewtons per meter squared. So that means our overconsolidation ratio, again, this is going to be dependent. It's going to change a bit, but it should be somewhere between 2 to 2.5. This value should be the same for everybody here, since this is based off of what the information is given you. OCR, this 310, this could change depending on how you decide to read this graph. So what we need to do now to find the primary consolidation settlement under load, we need to determine the delta sigma z. Now, you can decide which technique you want to use. I think the 2-to-1 method is the easiest. So using the 2-to-1 method, we have this equation. We're given the P, and then we're giving the depth as well as the length and the width. So what we get is a delta sigma z of 35 kpz when we plug that in, and we see that this is less when we add our in situ to our increase. This is about 180, which is less than our pre-consolidation pressure, which was 310-ish. So that means we are using a case 1 soil, or which is the OC, which stays on the CS. So remember, the CS curve is this part, the swelling index of our curve, and then once we go past our pre-consolidation pressure, then we have our CC, our coefficient of compression. So we use this equation, our case 1 over consolidation. We need our initial void ratio as well as this value. So to find these, we have to use our SE equals WGS, and all of that information is given to us. We know our sample is below the groundwater table, so we have 100% saturation. The height is 4 meters, and so this produces a 12.1 millimeters. Again, this could change a bit depending on what your 2-to-1 method, or what method you used here, and what or how we read our CS, as well as our delta, or our pre-consolidation pressure, which is not in this equation. But okay, so part 3, the elastic settlement of the sand layer under the center of the footing. So to do this, bowls would be the easiest method, and this is the equation for a flexible footing. So we need to go through and find all of those values. So we know it is the delta sigma, which is at the ground surface, is this 150. Our ES we need to find, so we can go to lecture 8, slide 8. You can use this equation. The important thing to note here is this alpha is dependent on the type of soil. It is not the same alpha as this one right here, so it can be kind of misleading. But yeah, this is for a clean, normally consolidated sand, should be about 10. Our average N60 blow count was 32, and then the atmospheric pressure, you can just assume 100 kPa. So this means our Young's modulus, or modulus of elasticity of the soil, is about 32,000 kPa. Again, this value could change a bit. Now, to find the geometric properties here, the center of the footing, was specified here. So the alpha is going to be 4 for our Bowles equation. The M prime and the N prime are going to be shown here. These are based off the geometry that is given to us. And for from lecture 7, we can use those tables to find our shape factor and our depth of foundation factor. So we get this equation here and we plug in everything, and what we see is that the KPAs would cancel. Don't forget to square this Poisson's ratio. And what we're left with here is going to be in meters. Now remember though, it was also specified in the drawing that this is a rigid foundation. So what we need to do is multiply this by 0.93 to get the corresponding settlement due to a rigid foundation. So that gives us about 10.14 millimeters. All right, problem number 2. So this one, we needed to find the CV from the hyperbola method, and then also find the estimated time for about 70% of the total consolidation settlement. So our equation for the hyperbola method is shown here. This is our coefficient of consolidation. So from lecture 6, slide 19, we need to plot on the x-axis time, and then the y-axis for the hyperbola method is time divided by the change in height. So the change in height is going to be the original dial reading minus each consecutive gauge reading. So what we should do when we plot this, and it's really important to keep track of all the units here, we'd have minutes over millimeters and then minutes here. And what we should see is this distinct hyperbola shape. So what we can do is just zoom in just only for this little specific section. And we can clearly see a trend here where we have a straight-ish line. And this is going to be our slope of this straight line. So that's rise over run. So the M value, as well as the D value. The D value is the intercept of this. Now this can change a little bit depending on if you actually eyeball it or actually put a slope and then find the Y-intercept. But what you should see is that your D value should be somewhere in 20 minutes over millimeters. And if you transfer this to different units, then the D value is going to be different, obviously. So for the slope, you just need to find the slope of this. You can pick any 2 points, or if you decide to use a trend line, you can find the slope that way. That means our CV value, when we plug everything in here, the slope is M, the drainage path is taken from the sample. So that is the 10 millimeters, since it's a 20 millimeter height sample. So it's doubly drained. And then, yeah, the D is 20 minutes over millimeters. So if you cancel all this out, you see we'll get minutes or millimeters squared over minutes. So to convert this to centimeters squared per second, we have to show the following. Now what we should get here is value. Okay, there it is. I'm sorry. 3.25 times 10 to the negative 4 centimeters squared. Now for the fourth part, or for part B, we're asked to find the estimated time required for 70% of total consolidation settlement. So we have to use this CV, so this is dependent on that. Our drainage height, since now we're looking at field conditions, this is 2 meters. Now for 70% of consolidation, we use a TV value of 0.403. We can plug everything in here accordingly, and we'd get this many minutes, or about 2.17-ish years. Okay, problem 3. This is a direct shear test result. You're asked to find the friction angle of the soil, the principal stresses, and the orientation of the failure plane for test 2, and then find the shear strength of the soil at a depth of 24. This is 30 feet. I don't know why I wrote 24. This is 30 feet down there. So what we first need to do is calculate the stress for each one. So remember, this dimensions were given you of 5 by 5 by 5 cube. 5-inch cube shear box. The normal force is shown there, and then it's a shear force shown vertically. So the shearing surfaces and the normal force surface is 5 times 5 inch, 25 inches. So we have to divide the normal force and the shear force by 25 square inches, each one, to get the units in pounds per square inch. So we have these values here, and this is what we would plot on our diagram here. So this would be our 30, or the normal stress versus our shear stress. And as long as the units are the same, PSI or PSF, then we should be okay. So what you need to do with this is two things. You could either put, or there's two options. You could either put a 0, 0 point here, or you could do a trend line, but you would need to set the trend line to have a y-intercept of 0 at this point. So if you didn't do that, then it would look something like that, maybe. Remember, since this is a direct shear test, we can only use sands, so sands must intersect at 0, 0 at this point. There's no cohesion. So what we need to find is the friction angle. The friction angle can be found this way. You can either take the average friction angle of each one of these using the tangent, or just take the tangent of the slope of this intersection, or the inverse tangent of that value. What we see, it's about 28 or 27.99-ish something. So we'd always round up and show the friction angle in terms of whole numbers, since we can't be too precise with this type of soil property. So that's our friction angle of the soil. The principal stresses and the orientation of the failure plane for test 2. To do this correctly and efficiently, then what you would need to do is plot this using some type of scaling technique, or just ensuring that your plot on Excel is actually square. And when I say square, I mean that the X and the Y dimensions are scaled together. So a perfect square should fit right here. So 5 PSI on the X-axis should be the same length on the vertical axis of 5 PSI. So once we have that, then all you need to do is fit a circle such that it intersects with the test 2 failure point. So once we have that circle, then you can determine the two stresses. And then once you have those two stresses, you can find the midpoint. And once you find the midpoint, you can solve for the angle right here, which is 2 times the theta f. Now you can use that, or you can also use this equation here. Remember, this was 28 was our friction angle. So 28 divided by 2, 14 plus 45, that's 59 degrees. So this would be our actual failure plane. So these are our principal stresses shown here, and then you can convert these into PSF, since that's normally what we're used to working with. And yeah, you can find the friction, or sorry, not the friction, the orientation of the failure plane accordingly. All right, so for question 3, 30 feet, 35 feet, I'm sorry, that's what it should say. So this is asked to actually find the shear strength of the soil at this depth. So remember, the shear strength using a more Coulomb is this right here. But since we're dealing with sands, this C value is 0 since there's no cohesion. So what we have is just this equation right here. So we've already found our friction angle. So what we need is our in situ vertical effective stress at 35 feet below the ground surface. Now we're given this table of all this test property, and since this is effective, we need to find the groundwater table is important. And all of these things are important to find the unit weight. So we know this friction angle. What we need to do is find our vertical effective stress at, I'm just going to say this point A, which is 35 feet below the ground surface. So right here we have 35 feet. we're told that the groundwater table is 5 feet below the ground surface, which means there is 30 feet here. So what we need to do is find our moist unit weight above the groundwater table, since it is saturated or 88% saturated above the groundwater table. And then what we're going to do is just assume that it is fully saturated under the groundwater table. So what you need to do is go all the way back to lecture 1 or back to your geotech and find the relationships given the specific gravity, the void ratio, and the degree of saturation to find the moist unit weight. So you should have a value of about 112 or 111.7 pounds per cubic foot. Now you can also find the saturated version of this by just plugging in 1 here, or you see a new equation shown there. Remember, the unit weights of water in these values are 62.4 pounds per cubic foot in these units. So once we have these, then we just go back to our Geotech 1 understanding of finding the effective stress. We have, again, this 5 foot of this moist unit weight. And then underneath that, we have 30 feet of this saturated unit weight. And since it is effective, we need to subtract out the pore water pressure. And that is 30 feet of 62.4 pounds per cubic foot, which is the unit weight of water. So what we have is an effective stress of 2341 pounds per square foot. We plug that into our Moore Coulomb shear strength equation. Sorry, this one, since C is equal to 0. And we get 1,245 pounds per square foot. So this would be the shear strength of the soil down here at this point A. All right, last one. So last one here, we said that the subsurface testing has identified a 9-meter thick clay layer that is overlain and underlain, aka sandwiched, by a highly permeable sand layer. So that means our drainage layer is going to be, or there's 2 drainage paths. So it's HDR is equal to H divided by 2. Now, a 3-centimeter thick sample of this same clay is prepared and tested in the laboratory under the same conditions, doubly drained conditions. If 60% of the settlement in the laboratory sample occurs in 4 minutes under this loading of normal pressure, what is the time required for 60% of the settlement in the field under the same normal pressure? We're asked to answer in years. So this is an interesting one, but a really applicable one because a lot of times in geotechnical engineering, we're testing things in the laboratory setting and we're using that information to then scale it up to the field setting. The benefit of taking clay or some undisturbed sample from the field and then testing it in the lab is if the behavior in the lab, since it's the same clay and we're using stresses, then the stress that we can reproduce in the lab should be indicative of the behavior of the field conditions. So what I'm going to do is just show like a little comparison chart here. So we have our laboratories testing and our field conditions. For the laboratory test, we know it's 3 centimeters. That's how thick the sample is. The HDR, since it is a doubly drained condition, then it's going to be 3 divided by 2. So that's 1.5 centimeters. Now we're told that it achieves 60% of the settlement in the laboratory. So that means our U, our degree of consolidation, is 60%. Now for that, our time rate of, or our time coefficient, our TV, is 0.283. And this can be found in lecture 6, slide 14. So to find our coefficient of time rate of consolidation, we use this equation here. Now we were told that it is 4 minutes. So we can plug that value in. We need to keep track of our units here though. And what we get is a centimeter squared per minute. So we have a CV value of 0.159 centimeters squared per minute. Now this CV value is a material property, which means the laboratory setting, or it doesn't matter how we find this, like this material, this value here is a property of the clay. So we're using the same clay in the field condition. So we can use that to understand how the field is going to react under similar loading. So for our field condition, we have 9-meter thick layer of clay, and it is underlain and overlain by permeable sand. So it's sandwich, which means it's doubly drained. I'm just going to put it in the same units here just so we can correspond it with our CV value. So we're asked to find the time required for 60% settlement. So all we need to do is just rearrange this equation here. We are using the same CV, right? Because this is going to be a soil property. So we can just solve for our T. I'm going to put the units in here again so we can make sure that they cancel out here. So this 450, don't forget to square that on the drainage side of things. So centimeters squared, centimeters squared. So this is 1/1/minutes. So 1 divided by something that is being divided by. So that it means that bumps it up to the numerator. And what we see is we get a value of 300,006, whatever this thing is. Big number here. So what we're asked to do is answer this in years. So we can convert this accordingly. 1 hour, 60 minutes, 24, or 1 day, 24 hours. And then 1 year is 365 days. Minutes cancel, hours cancel, days cancel. What we're left with years now is about 0.693 years ish, or about like 2/3 ish of a year. This would be the answer for this one. Pretty straightforward. I guess the only about reason it should change a little bit is if your TV value changed. But again, this is really important in understanding geotechnical engineering. We use lab testing to find soil properties, and then we can use that soil property to understand the field conditions or the field behavior. All right, if there's any questions on the exam, I'd be happy to answer them in more detail. Or once read through, I'll leave as many notes as I can on your graded exams, and I can go through the grading scheme. But be on the lookout for that later this week. All right, let's go over the project details. So by now, if you go on Canvas and you click on the project little tab there, then you should see more information on this. Basically, the overview of this project is you're going to research and present an innovative foundation design solution. I've mentioned this in class multiple times, but in class, we're only able to cover just time-wise shallow foundations and deep foundations. But what you'll see whenever you start getting to work in the geotech world or start working with geotechs is there are many, many, many more different types of foundation design solutions. So a lot of these are kind of tried and true. They're not even considered innovative anymore, but each one could have their own specific type of class that you could cover. So you guys are going to be divided into groups, and I will automatically just randomly select those through the power of Canvas, randomly selecting people. And then you're going to research and present a short paper on one of these topics. And you can choose topics that aren't shown here, but these are just some of the examples of very common things that you'll come across. Auger cast piles are really popular in Florida. There's a lot of research going into that. A lot of, it's kind of quick construction that doesn't require a lot of prefabricated piles. Deep soil mixing, TRD, this is used a lot. It's basically, you can think of deep soil mixing as like an underground fence that they're basically installing. Not like a sheet pile wall, but like down in Lake Okeechobee, they use this like to create an impermeable layer, like basically an underground fence of concrete to stop water flow. Stone columns, we mentioned that in CE materials. This is also used a lot in areas where there is a lot of groundwater movement, and you can't block those. Helical piles, those are good for tension support as well. Drilled shafts, suction casings, offshore and onshore wind turbine foundations. These are freaking crazy. In Norway, they do a lot of cool stuff. You can look up there for these massive structures, like the largest geotechnical engineering structures. And you can also do foundation designs for famous large-scale projects. There's a lot of ASCE case histories up there, like floating around. As I mentioned, probably in the past. Geotechnical engineering is kind of unique because we just need to learn from the mistakes of others, because it's just kind of unfortunately very much so trial and error um, discipline. So yeah, ASCE, American Society of Civil Engineers, the GI, the Geo Institute, they publish a lot of famous large-scale project case histories, so they can learn for future projects that might be similar. So the Burj Khalifa, the Brooklyn Bridge is another really famous one. Golden Gate Bridge, the design for that is pretty famous. So you can look into those in more detail too. So what the project will actually look like, and there's a sheet that you can download, but it will consist of a research report about 5 to 10 pages, and this is going to be submitted as a group. So this is, you'll see Canvas under the people section, and then your lab, or your not lab groups, your research report groups. Going to have an introduction, brief history on the topic, governing design codes, if any, the benefit for the foundation type. So why, like what type of, or when or why would you want to use this type of foundation? Potential issues with the foundation type. So is it super expensive? Contractors required, time to construct, still innovative and not really known about, that kind of thing. And then specific examples of use. So why was this foundation chosen? Subsurface information, Google Maps, and pictures of like little mini case histories. So that's going to be the overline. There's more information on Canvas for that. Then what you can also do is, this is an extra credit opportunity, but this is optional. Individually, what you're able to do is record a short, like 5 to 7 minute presentation about your specific topic. So you're going to overview the topic and application and also discuss what you learned about this. Now, this is on an individual layer. So like you can't be just submitting the same PowerPoint and reviewing it. So this is, again, optional, extra credit, but I understand that a lot of these research reports, when you're working in groups, sometimes people might work harder than others. So if you feel really confident about your research project and you did a lot into it, then you can make a quick presentation explaining that, and you'll be able to get a little extra credit on there. So what you need to do after this is posted, go on Canvas, review your group, your project groups, and then pick a topic. You'll see a discussion forum that will be on Canvas, and then it'll just be like first come, first serve. So you will post like, we are group, blah, 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 and then write down your topic that you want, and write like a second topic too, just in case somebody clicks post at the same exact time as you. So yeah, please reference that. We'll talk more about it, I guess next week, because we won't meet this week with the fall break and this being out. I appreciate you guys being flexible again with the course. I will see you guys on Monday, and enjoy your week and the freezing cold weather that's coming our way. All right, guys, send me an email if there's any questions or issues. I'd be happy to answer them. Take care.